And rounding out our speakers for today, we have Dr. Hari Arthanari. Dr. Arthanari is an associate professor at Harvard Medical School and Dana-Farber Cancer Institute. His expertise lies in leveraging NMR techniques to elucidate the structures of proteins and nucleic acids and to probe their interactions. His research endeavors extend the capabilities of NMR spectroscopy to investigate the large and intricate systems, aiming to address targets previously considered undruggable. Dr. Arthanari's lab uses a structure-guided methodology to dissect, validate, and manipulate protein-protein interactions within a therapeutic framework employing an integrated suite of technologies. This comprehensive approach allows them to map interaction interfaces at the atomic level and pinpoint druggable hotspots. By delineating the molecular dynamics of these interactions, his lab aims to discover innovative inhibitors that could potentially transform into therapeutic solutions for associated diseases. His talk today is entitled Fluorine as Atomic Beacons for Probing the Structure and Dynamics of Large Biomolecules. And without further ado, Hari, the floor is yours.
Thank you, Kelly. And I'd like to begin by thanking CIL and Kelly for the opportunity and also for providing us with these lovely isotopes, which is the cornerstone of many NMR investigations. And today I would like to talk to you about using fluorine as an atomic beacon for probing structure and dynamics of biomolecules. And this is especially important in the age of de novo structure predictions, where the NMR can uniquely provide information about dynamics, alternate states, which could be then used in a therapeutic context. Now, if you look at the use of solution NMR, as the size of the protein increases, the number of probes that we have decreases. So when you go from a 10 kilodalton protein, where pretty much every atom in the protein acts as a probe, when you go to a 30 kilodalton protein, you go to deuterated, and that restricts ourselves just to the amides using the TROSY effect. And you go to about 100 kilodalton protein that Eve showed, then you'll restrict it to the methyl groups. And what this leaves is the aromatic residues, which are often the cornerstones of the protein, especially forming the protein core, involved in enzymatic active sites, and as hub for interactions, rather as a blind spot when we go to larger systems. And our idea is, can we use fluorine to eliminate these blind spots of aromatic residues in a larger system? And the use of fluorine in biomolecules has a long history in NMR, pioneered by different groups, Angela Gronenborn, Tatiana, Scott Prosser, Gottfried Otting, Kurt Wuthrich, and Will Pomeranz and Mei Hong in solid-state NMR. Well, the unique advantage is actually, in fact, if you take the history of using fluorine, especially in aromatic residues, can be dated back to 1961 when Westhead and Boyer fed poor rabbits with 4-fluorophenylalanine, and they were able to assess the enzymatic activities of these fluorine-incorporated amino acids right from a rabbit's serum. Now, I think I'm preaching to the choir here. Fluorine has some unique advantages when it comes to NMR. The first thing is the bio-orthogonality. Is the idea is that the atom fluorine is not present in most of the biological systems, so it gives us a unique probe when you're looking at it in the milieu of other things. The other advantages include the relatively high gyromagnetic ratio, the 100% natural abundance, and for me, the most interesting part is this intrinsic sensitivity to its electronic environment that results in a wide range of chemical shifts, and the sensitivity of the chemical shift can be used effectively to probe interactions and other things. But what restricts the use of fluorine in bio-NMR is chemical shift and isotropy, which looks rather like an American football than a European soccer ball. And what this causes is faster relaxation of the fluorine, especially in high molecular weight systems or at higher magnetic field strengths. To illustrate this point, let's look at a toy molecule, which has an aromatic ring. What is in cyan here is the fluorine atom. And then you'll have the other elements in this toy molecule that will typically find in the protein, a carbonyl atom, an amide group, and a methyl group. Now, if we have to plot the CSA tensor, which we did it with the help of Ilya's spinach, that will look like this. And what looks like a giant Death Star for you here in pink is the CSA tensor of fluorine. And now that compared to the other CSAs that we normally encounter looks pretty daunting. To put this in more into a perspective, here, the typical CSA that we complain about in proteins are the carbonyl CSA and the aromatic CSA that's plotted, especially what's the contribution of the CSA to the transverse relaxation rate on the y-axis is plotted as a function of the magnetic field strength. But now when I include the fluorine CSA or the contribution of the CSA to the relaxation, these look like little angel. So this CSA-induced relaxation prevents the use or hinders the use of the fluorine atom in high molecular weight system. So the question we are interested is that can we somehow mitigate this effort, this fluorine-induced, the CSA-induced relaxation of fluorine by some of the standard techniques that people have tried before, which is essentially using some cross-correlated relaxation mechanisms, similar to what we find in an H-TROSY, aromatic TROSY, or in the methyl TROSY that was developed by Lewis K. So we did some theoretical calculations, and we find that when a fluorine is attached to a carbon in the context of an aromatic ring, the TROSY effect reduces the relaxation of the carbon, essentially using a correlation between the dipole-dipole and the CSA. And here we show the relaxation, which is plotted on the y-axis as a function of magnetic field strength. The TROSY component relaxes slower when the carbon is attached to a fluorine. Actually, that you compare this to a CH-TROSY effect previously established by Kurtwoodring and Pervushin, we see a much slower relaxation compared if the same carbon is attached to a hydrogen. Whereas this TROSY effect is not found on the fluorine side because it's dominated by its own CSA relaxation. So essentially what we did was we solved half the problem. So we couldn't mitigate much of the CSA-induced relaxation of the fluorine, but the idea is that can we disperse this broad signal using the carbon signal, which now relaxes slower if we choose for the TROSY component. Now, the question is that you have to make this particular C13F19 labeled aromatic amino acid. And there we actually took a page from Scott Prosser's playbook where we leverage the acidity of this particular hydrogen in a tyrosine, a precursor that you can get from CIL using select fluor. And you can get this amino acid made by Vlado Gillip, where this carbon is attached to a fluorine. And if you incorporate this amino acid into a protein, what you can see is that you can actually measure the CF-TROSY and the CH-TROSY on the same molecule. So how do we do this? We actually take our bacteria, we grow it, we add this thing called glyphosate, which inhibits an enzyme in the corazimate pathway. So the bacteria is no longer able to make the aromatic amino acids. So we go to supply them. And here we cheat and we supply one of the amino acids as a fluorinated amino acids and the other three as the other two as non-fluorinated. And the bacteria is able to incorporate this with a reasonable efficiency over here. So what Andras did is take GB1, our favorite protein, and then use the C13F19 labeled tyrosine. And GB1 has 3 tyrosine, and it's a relatively small protein, it's about 6 kilodaltons. And you can immediately see the TROSY effect right from a simple 1D carbon spectra. And here we'll see 3 pairs of doublet, and the doublet are shown over here with a 240 hertz coupling. And you'll see one of them is extremely sharp compared to the other. And the small coupling you see here is a carbon-carbon coupling between this carbon and the other carbon, but you can immediately clearly see the TROSY effect. Now, this TROSY effect is not only enjoyed by just the substitution of the tyrosine, but if you substitute the fluorine at any positions in the ring, you get a phenomenal TROSY effect. And in some cases, the relaxation almost goes to a single-digit number over here. So different substitutions are possible, at least from our theoretical calculation. So now how do we record the 2D correlation between the carbon and the fluorine? Typically, textbook says that you have to start with the high gamma nuclei and end with the low gamma nuclei, end with the high gamma nuclei. But here what we did was we want to keep the fluorine in the transverse plane as short as possible. So we went with an out and stay type pulse sequence, either starting with the fluorine or starting with the carbon and ending with the other nuclei. And we used the classic ST2PT pulse sequence to choose for the TROSY component. And the reason is that whenever fluorine is transverse, you can see over here the transverse relaxation rate, color-coded by the contribution from the CSA and the dipole. Whenever fluorine is transverse, these are the typical coherence you will find in a TROSY pulse sequence. It relaxes extremely fast. So we want to keep fluorine transverse for as less as possible. Now we get this beautiful 2D correlations. Now we move to the protein MBP, and then you can see that neither the 1D carbon nor the 1D fluorine, you're able to separate all the resonances, but in this 2D correlation of carbon fluorine with the TROSY selection, you're able to get very narrow lines on the carbon that separates a broad line, and you get a fantastic resolution. Here's a comparison of the CH TROSY with the CF TROSY on MBP at 25 degrees, and we can make the protein tumble slower, mimic a larger protein by just dropping the temperature. And when you drop the temperature, we get still phenomenal resonance with the CF TROSY, but in the same protein, the CH TROSY doesn't look that good. And again, this is a testament that when you attach to a fluorine to the carbon, the relaxation rate is when you choose the TROSY component of the carbon is extremely slow. That gives you a fantastic resolution. And we were able to show this on the 180 kilodalton alpha 7 subring 20th proteasome subunit. And here you can see the aromatic resonances for the first time in this large protein. Now, this was tyrosine, and the tyrosine has one, let's say, one problem. The problem is that aromatic rings are known for their ring flips, started with the work of Gerhard Wagner. And what happens is that when you have a regular tyrosine, the ring flips are symmetric. Let's say there are two environment that the protein sees. And if this is a hydrogen, if it flips, it's pretty symmetric. Whereas if you have a fluorine on one side, the ring flips are no longer symmetric. And then we see some of the tyrosines in one place and the others. So this is one of the issues with having the substitution of the fluorine at this position on the tyrosine. The second problem with this particular um, uh, approach is that the TROSY effect is only enjoyed by the carbon, whereas the fluorine always relaxes faster. Now, this is so now we're trying to record a two-dimensional correlation, and this is similar to a relay race where one of the person is like me running really slow, and then even though Hussein Bolt is on the other side, which is the carbon, who can run very fast, relaxing very slowly. The problem is going to be that in one dimension, you're still going to have a pretty high line width. Now, to mitigate this problem, we thought of another approach. So at first, we thought of going to phenylalanine and putting the fluorine that is attached to the carbon at this particular position. Now, this makes the ring flip symmetric. And then we thought that if there's a hydrogen at the meta position compared to this particular carbon, so instead of doing a carbon-fluorine correlation, we can actually use the long-range coupling between this hydrogen correlate to that carbon and yet choosing for the TROSY component with respect to the fluorine. Now you have a very narrow line and you have an isotropic nuclei over here. And then you can correlate this to get extremely narrow lines. So that was an idea over here. And in order to do that, we went back to our friend Badou Gelov, and to prevent or to slow down the relaxation of this meta hydrogen, what we did was we deuterated this part, which is the closest dipole to this. There's no hydrogens over here. So we deuterated that so that we can slow down the relaxation. So now we can correlate the hydrogen here with the carbon attached to the fluorine. And first, let me show you here the protein of choice was human carbonic anhydrase. We get fantastic carbon fluorine correlations using the TROSY effect, both at about 25 degrees and at about 5 degrees. The protein is big, but we can still see very sharp lines. But the idea is that now to correlate this hydrogen with this particular fluorine, the coupling is about 10 hertz. Now, the way we did that, what Abhinav, and yet you have to choose for the TROSY component of this of the carbon fluorine or the carbon with respect to the fluorine. So we do a simple head core experiment where we transfer magnetization from this hydrogen to the carbon, and since the coupling is small, the transfer time is large. So we leverage this to encode the magnetization of the hydrogen during the transfer time in a constant time manner. So at the end of this first transfer, you're antiphase, you're on carbon, but antiphase with respect to the hydrogen. All you do is wait for it to refocus, and then you can detect on carbon. That was the idea. And during this waiting time period, we thought we'll put a 180-degree pulse in an in-phase antiphase approach, where you get the carbon signal split by this fluorine coupling in either an in-phase or an antiphase manner. And if you add the spectra or subtract the spectra, depending upon how you phase it, you can choose for the TROSY component. So when we recorded the spectrum with this particular approach, to our surprise, we just saw one signal. We didn't see the other antiphase signal. And then we realized that since the transfer time here is rather large, what happens is that the non-TROSY component actually relaxes very fast. And we're able to show this in a simple 2D experiment with an HC correlation, which just appended a delay. Now you can see that there are two resonances, the TROSY and the anti-TROSY. When you increase that, the anti-TROSY automatically relaxes off. So the idea here is that you can actually beautifully record an HC correlation, choosing for the TROSY component, and you don't even need an F19 probe. You can actually pulse it without F19 probe. You get this for free. So now the question is that, so here I show you two different correlations on human carbonic anhydrase. One is the carbon-proton correlation that I talked about, and the other is the carbon-fluorine correlation. Now you can see the carbon line, which are pretty much similar on both spectra. That's shown over here because we're looking at the same TROSY component. But you can see the fluorine line width is about almost 20 times larger than what you see with the proton line width. So if you define resolution as a line width, you get fantastic line width when you take an isotropic spin. But if we choose the word resolution as the ability to see the peaks clearly, the fluorine chemical shift is spread over 10 ppm, whereas the proton chemical shift is only spread over 1 ppm. You're still able to see things clearly. So at this point, it becomes a philosophical discussion on which one you want to use. Now, Sebastian was able to take this to again, this HC correlation to a larger molecular weight system. Here again, we went to the 182 kilodalton proteasome. You see a nice comparison of the HC correlation, very sharp lines with the carbon fluorine correlation. And we can also drop the temperature to about 35 degrees where it tumbles as an 85 nanosecond. And you can see phenomenal correlations for the resonances for the aromatic residue. We're also able to do this. So now the previous methods that I've described where we add the glyphosate incorporates a carbon fluorinated aromatic amino acid at every occurrence of that amino acid, which means every tyrosine in your sequence would be a carbon fluorine label. But we can also enable the incorporation at a site-specific location, especially in the case of phenylalanine, 4-fluorophenylalanine, using the codon expansion technology, and we collaborated with the group of Ryan at Oregon State University. And here, using an amber codon strategy, we are able to produce a protein which has C13F19 labeled amino acid at a single position. Here, the protein here we use is GFP, and here we show the correlation of the carbon with respect to the fluorine and the carbon with respect to the hydrogen. Now, the question is that if you have a single fluorine, why would you need a 2D is a question that you might ask. So we can use this kind of idea where you have a single amino acid in multiplexing. Let's say you have a bunch of kinases that you want to screen against. So you can actually put them together with a single fluorinated amino acid at the binding site. And they will have different resonances because they are going to, or different resonances appear at different frequency because of their unique status and where they occur in the structure. And now you can add a small molecule and see how selective that small molecule to the kinase that you're adding. So that's one advantage that you have here. I'd like to finish off saying that this idea that you can mitigate the CSA-induced relaxation of fluorine by dispersing the broad fluorine signal using the carbon is not only unique to proteins, but it also found in nuclear bases. And we've shown that by theoretical calculations that different substitutions in different places in nuclear bases gives you very narrow carbon lines. And this was beautifully leveraged by Christoph Kreutz and Kwaku in a series of publications where they are able to incorporate these carbon fluorine labeled nuclear bases either by synthesis or by in vitro transcription into different RNAs and get very, very narrow lines. So here is the summary. Given the time, we have access to several carbon fluorine labeled amino acids, or aromatic amino acids. We have published on tyrosine and phenylalanine, and especially in the case of phenylalanine, you can look at the hydrogen carbon correlation as well. And I think you can get these two from CIL. And recently, there's another publication by Lichtenstein from Austria, where the whole thing is deuterated. And Lichtenstein and Scott Prosser also have a way of labeling C13 tryptophan. So you have both tyrosine, phenylalanine, and different variations of tryptophan that you can get 13CF19 labeled in. So this provide opportunities to probe structure, and especially the fluorine has a way of giving dynamics information in the lower microsecond timescale, previously exploited by Scott Prosser. We have a few assignment strategies that I don't have the time to present today, but it's detailed in some of our papers, or we can go through that as well. And the proton carbon fluorine TROSY, which is the correlation between this hydrogen and fluorine, gives the best of both worlds. And here deuteration helps because that helps the remote protons to this hydrogen relax, make this hydrogen relax slower. With that, I would like to thank the people who did the work. Andraz was initially spearheading the project. Sebastian was key in improving the incorporation rate using several techniques. Abhinav and Thibault for the various works on the pulse sequences, with help from Veronica, Sandeep, especially the codon expansion team at Oregon, and Gerhard and Co for their help and advice. Most of the theoretical calculations were done by Ilya in spinach, using Ilya's spinach, and the synthesis of these were spearheaded by Vlado and Denny at Sofia University. And for a long time, we didn't have a fluorine observed probe at HMS, and we had to collaborate with Bruker, who were kind enough to give us time. And I'd like to thank Wolfgang, Helena, and Clemens for their help as well. And finally, I'd like to leave these things for a long time. The aromatic amino acid have been neglected. We've been concentrating on amides and methyls. I think some of these methods would give the much deserved love to the aromatic amino acids. I'd like to thank you for your attention.
Wonderful. Thank you for an excellent talk showcasing really the utilization of 19F and all the possibilities that it can give us in the NMR community. So thank you very much, Hari. We do have a few questions in the chat. How does T2 relaxation rate affect in a CF3 group attached to an aromatic ring with respective to F directly attached to the aromatic ring?
So I can parse this question in two different ways. The first is there a TROSY effect akin to the methyl TROSY effect that people have observed, which is a dipole-dipole cross correlation. And there's a lovely paper by Brian Sykes, and we have also done the calculations, and there is not a TROSY effect similar to a methyl TROSY effect. But what you're going to see in a CF3 is that the fast helicopter motions of the CF3 groups are going to help you just in just the T2 by itself, because they rotate independent of the molecule. And you have three fluorines, so that's also going to give you more sensitivity. So that's a yes on that, but there is not a TROSY effect. And it is also a little bit more, the one thing to keep in mind when you're doing this fluorine substitution is they're not as benign as substituting with the metal, where you're just replacing a C12 with a C13. Here you're adding another fluorine group. So one should always bear in mind as to what the impact of the substitution on the structure or the dynamics that you're observing. Is the dynamics germane to the protein, or is it because of something that you introduce, is a question that we always have to keep in mind.
Awesome. Thank you very much. One other question that we have is, how do you deal with the 19F relaxation for molecular weight greater than 20 kilodaltons on the 19F proton HOE, I think it's NOSY experiments?
The 19F, there is no easy way to get away from the 19F relaxation, because even deuteration doesn't help, because the 19F relaxation is largely governed by its CSA. Now, if you're talking about the HOSY experiment, which is the heteronuclear NOE between proton and fluorine, that's a rather insensitive experiment. And here, I think there is probably initial work from the group of Fabian and Faraj, where we see that probably lower fields would help it. But this experiment, I think Sebastian Schindler and my group had tried different variations of this. It's rather insensitive for especially working with weak, lowly concentrated protein that are relaxing extremely fast.
Awesome. And we do have two more questions in the Q&A box. Would you be able to type the answers to those so that we can
Sure.
conclude? I think we're ending pretty much close on our time. Thank you. Alrighty. And with that, we're approaching the close of our isotope day, the NMR section. So I want to give a huge thank you to all of our speakers, as well as to all of you in the audience for your active participation and attentiveness throughout today's talks. And to recap the goals we aimed to achieve in today's webinar, I think we really did see the breadth and scope of stable isotope applications within the NMR field, and I think we can all agree that we had many new insights shared from our panel of speakers. I hope that you are all able to strengthen your understanding of CIL's products and how they can be used in the field, as well as how CIL can support you as a research partner and supplier in all your different research areas and applications. Once again, thank you to our outstanding speakers and for the talks today, and thank you all for staying engaged throughout and also for your active participation in the Q&A sections as well. We'll go ahead and leave a little bit of extra time so that the speakers can finish answering your Q&A questions if they weren't able to get answered to live. But once the session is closed today, a general survey will come up, and we appreciate your feedback for what you liked, what we could do better going forward for future renditions of our isotope days. We will also send out a follow-up email with links to today's talks as well as relevant information. And for questions or product requests, you're always more than welcome to reach out to us at our CIL sales or visiting us at isotope.com. And if you're interested in watching the renditions of the talks that we had, whether it be from the MS, NMR, or our upcoming environmental isotope day, you can go ahead and scan the QR code and register and be able to see all of the talks that we have permission to share after the fact. So once again, thank you for all your time and your attention, and we look forward to working with you in the future. Thank you all for being present here today with us, and thank you to our speakers and attendees once again.